say where the domain of definition is. All I said basically is that, yeah, you know this f of x, y, and if in this rectangular region over here, f of x, y, and partial y are both continuous, then you give me any point in that region. It could be here, it could be here. A solution, a curve will exist that goes through that point. But notice how I stopped it short over here, okay? Okay, I'll give you the question is, does it go outside the rectangle, stay in the rectangle? This is what's called a local theorem, okay? It really isn't too useful in practice because it doesn't tell you, how far the solution goes. Maybe if this is maybe this is like say the point 3, 3. Does it just go to x equals 4 and x equals 1? Or does it go for x going to plus or minus infinity? Okay? So you notice basically that I purposely did not draw that black curve, going into the border of the rectangle. Okay? Because what can happen is we'll see as we do some problems, you can develop these again vertical asymptotes. Okay? But all it says is that if these conditions are satisfied and you take your initial point somewhere in that rectangle, yes, a solution curve will go through that point. How far it goes, though, this theorem doesn't tell you. Okay? And the reason it's kind of vague in that way is that it's a very general equation, dy dx equals f of x, y. Okay? If we had a linear equation, you'd get much, much more precise information about it. Because a linear equation is more specific. And that's true all the time in mathematics. The more general you are, the less you can say. Okay? Because it covers so many cases. Okay? But even for a nonlinear one, okay, so long as these conditions are satisfied, you'll be sure that there's a solution. Okay. That's unique. So the question is, what went wrong over here with these two guys over here? Obviously something didn't go through, right? Because this thing says if these conditions are satisfied, then I should have a unique solution. Okay. So let's just go through it slowly, okay? Let's apply this theorem over here. F of x, y is y. That's the right-hand side of the differential equation. So that's going to be x radical y, right? Remember, the first thing that we have to look at is f of x, y has to be continuous, okay? Where is f of x, y continuous over here? X is okay, but radical y requires what? Y has to be greater or equal to 0, okay? So f of x, y equals x radical y, continuous only if y greater than 0, but the x is fine. Minus infinity, less than x, less than infinity. Okay? So to get a picture of this thing, what this thing says over here, as far as f of x, y is concerned, it's continuous everywhere in the upper half of the xy plane, even including the x-axis. As long as you're above the x-axis, you're okay. Below, no, because y becomes negative, and f of x, y is not continuous there. Okay. Y greater than or equal to 0. Very good. Yeah, y greater than or equal. Thank you. Y greater or equal to 0. Because you can take the square root of 0. Yeah, very important point. Thanks. Okay. However, what's the partial of f with respect to y? Okay, remember I take derivatives, you keep x fixed. It's really derivative of y to 1/2, which is 1/2 y to the minus 1/2. So it's 1 over 2x. Where's partial f, partial y continuous? Again, I can't have x equal to 0. Furthermore, I must have y greater than 0. Right? And x not equal to 0. So this is why basically this thing failed. Okay? Why the theorem didn't go through. Because the theorem says f of x, y has to be continuous. Okay? Well, that just means upper half of the xy plane, including the x-axis. But partial f, partial y to be continuous requires y to be positive. And look where the initial condition was given. It goes through 0, 0. 0, 0 is right over here. And at 0, 0, partial f, partial y doesn't exist. Obviously, it's not continuous. Okay? So if we have an example, basically, that where we have not a unique solution, clearly one of the hypotheses in this theorem, either one or both, in this case it's the second one, is violated. Okay? However, what does this theorem say? It says for this particular problem, dy dx equals x radical y, if I gave my initial condition any point in the upper half of the xy plane, okay, then a solution exists. So, by theorem, unique solution exists for any initial point right? Provided, again, you want x naught not equal to 0 and y0 positive. Okay? So for example, if I would go over here, or over here, or over here, or over here, right? There's always be a curve that goes to that point that solves the differential equation. But again, we don't know how far it goes. Okay? So it's what's called a local theorem. Okay? Someone have a question on that? Or, okay, hopefully, yeah. Okay. Okay. So, just, something to mention, okay? And I think some of the homework asks you, giving you like some problem and say, look, here's two solutions, and then it'll ask you, why did this theorem apply? And you'll find that either this fails or that fails, or perhaps both. Okay? Okay. Now we have some fun, okay? I'm going to basically, these are a bunch of, kind of a survey of mechanical engineering problems that, you'll come across, and we'll set up the differential equation, okay? These are the whole math models. Okay, so the first one, we're going to do basically a flowing body. And a uniform gravitational field. Uniform body and a uniform gravitational field. You will have done this in physics courses, okay? Actually, one of the things which is going to be really interesting is towards the end of the course, I'm going to look at, we're going to look at a rocket where it's being launched, and the question is there, is that you can't assume that the gravitational field is uniform. Right, drops off as 1 over r squared, and we're going to look very carefully of this model, the one where it's a uniform gravity field versus the inverse square. We're going to look at some interesting, differences and contrasts there. But in this case, basically, here's the situation. We're near the surface of the Earth. Okay, so it's like, baseball or something like that. How far can you, even if you're Mickey Mantle, how far can you throw it, okay? And we'll call S positive upward, okay? Remember, you take your origin of coordinates, it's arbitrary. So let S equal to 0 equal the ground, assume the ground is flat, S increasing up there. And at T equal to 0, we'll assume that the body's like a particle, and it's at a height S naught, and has a velocity V. We know what's happening, right? Depending on how big V naught is, it's going to climb and climb and climb. Finally, in this case, you have 0 velocity, that's maximum height. It'll come back towards the ground. Okay. So, what's the governing equation over there? So Newton's law, right? Net force equals mass times acceleration. Okay? So we have the mass. What's the acceleration? It's the second derivative with respect to time. And the net external force on this thing, the only thing that's acting is going to make a free body diagram, okay? The only thing you got is a little mg down. Be careful of your signs because, this is really a vector equation in one dimension. So S double dot positive going up, so we need a minus mg. Or the n cancels, second derivative with respect to time is minus g. Okay? G is approximately 32 feet per second, 9.8 meters per second. And actually, this one is so easy to integrate it without this force. Okay? We integrate, we find that ds dt is equal to minus gt plus an arbitrary constant of integration. Remember? We always have constant integration when we get that integral. How do you get that? Well, you put in some data. Okay? At t, I should say, over here we have two conditions. At time 0, that's when we release it, we'll say that the velocity, or s dot, is v naught, and s equals s naught. Okay? And that's perfect agreement that we know that for something like this, we need the initial position and velocity. So, you integrate this thing, you get this guy, plug in t equal to 0, well, t equals 0, no ds dt, it's v naught. Okay? So therefore, this differential equation becomes ds dt equals minus gt plus v naught. Okay, so we got rid of that constant of integration, got a definite value in terms of the initial speed. Now we integrate once more to get the distance as a function of time. We get minus g t squared over 2 plus v naught t, and then another constant of integration, c sub 2. But now I'm going to measure S this way. It doesn't make a difference, just makes the math easier. That's positive S. So you're like going above the ground, okay, dropping it, okay? Well, now, when I make a free body diagram, I've got mg, right, acting downward in the direction of positive S, and I got a viscous force over here, okay, minus k, actually v to a power, v to the p, okay? Because what happens is that modeling aerodynamic drag is not too simple. Sometimes you get along with a model that's just proportional to the speed, but when you get higher and higher speeds, the drag on the particle may go up to v squared, some fractional power, okay, of the speed. So all this says is that the viscous force acting, or the drag force on the particle, is proportional to some power of the speed, okay? And again, k positive, right, because it's opposing the motion. Okay? Now when I do Newton's law, I've got m times the second derivative of s with respect to time, mass times acceleration, equals net force acting on the particle. Okay, now positive s is down, so I got mg minus k times the square of the speed of the ds dt to the power. Okay? And if you want to write a little differently, it says m second derivative of s with respect to time. Let's bring all this up with s on one inside, plus some positive proportionality constant, ds dt to some power p equals mg. Okay? And that equation is hard to solve if p is not equal to 1. And if p equal to 2, we're going to do it, but it's not so simple. Well, p is a fraction, it's even worse. Okay? So there's two simple, kind of problems basically showing you how differential equations just naturally arise. Okay. Oh, next one I want to do, now this one I'm going to do different than the book, okay, because they kind of cheat on this, okay. And since we're mechanical engineers, I just want to do this a little more rigorously. Okay, next problem I'm going to do is derive the differential equation for a cable that's hanging in equilibrium. So this could be like a rope, say I anchor once over there, one to the other wall, okay, or telegraph type poles, and there's birds sitting on it, or wind, okay. So we're going to do a pretty general problem, namely of a flexible cable, okay, fixed at both ends, and find the differential equation that describes how it hangs, okay. So this will be the hanging cable problem. Like I said, the book kind of cheats on this, okay?
Professor?
Yes.
The differential equation describes the actual curve?
Yeah, well, yeah, exactly. For the cable, yeah, if you were able to solve the differential equation, which we will by the end of the course, you'll get the actual curve that you can plot. Okay? So here's the situation base. I've got this over here, okay? I've got a support, doesn't have to be the same height. Maybe it's going over here. And the cable just hangs under its own weight. Okay? This point A. Yep, too many points. Okay? You know the distance between the two and P is the cable. Now this is something you do in all your courses. When you want to derive differential equations, what's called continuum, okay? You have to make certain assumptions, okay? What happens over here is I'm going to make some assumptions that cable is perfectly flexible. What that means, basically, is that I'll give you two extremes. Imagine like a very, light rope, okay? If I try to take the rope and I, try to torque it at the ends, it doesn't offer too much resistance. If I had a real heavy steel beam, okay, and I put torques at both ends, and I try to do it, I've got to put a really strong torque on there to get it to deflect, like I did before. That's what's called the bending stiffness, okay? And when you do beam theory, it's much more complicated in cables because you need what's called an internal bending moment in the structure, and not just a tension, okay? We're going to assume also that the cable is thin, and the tension acts in a tangential direction onto the cable. And that'll be best illustrated by a little diagram. Okay? See, the book doesn't spell these things out. Okay? There's a lot of assumptions but let's keep this simple problem over here. Okay. So what we do is, here's the kind of situation over there. These are the boundaries where it's supported on these, posts or whatever. Okay. The way you derive this is be useful to you in many courses that you take. Why we clutch over here. The way you derive this is you go in there and you take what's called a mathematical section of it. Okay. You basically cut it over here and over here. Well, what does that look like? Basically, I've got something that looks like this. We'll call that endpoint B and call that endpoint A. Okay? So AB is a section of the table. Okay? And now we're going to use Newton's law of equilibrium, and recall that when you use Newton's law either for dynamic equilibrium or for static equilibrium, you have to include all the forces acting on that piece. Okay? Now the fact that I've kind of extracted this piece from the table, I've got internal forces on that, right? Obviously, that's why it's supported, right? Now the question is, what's the nature of those forces? Okay? I'm going to assume, based upon the second assumption,